is a little different too. Got to use that, well, because the TLB, and then you could either do that or the mix it with an LRU. And well, we have to use that backing store as like a disk, simulating like a disk and pulling information from it, putting in the, bringing the page out. You know?
Do we have to code it in C?
I believe so.
Why? We're not actually writing the software. We're just writing a simulator. You don't need that in C.
Well, no, email him, ask him.
I want to write in a real language.
I'm doing mine in C.
Hello.
Hello.
You can see the desktop, right?
Yes.
Okay. I finally updated some. Let me see. There. Okay. There's what's up there right now. Okay. I took the code that I've been working on. I broke it up into 4 different groups because there was really like 4 different things that they were doing. So to make it a little bit easier to digest it, I put the code into 4 different zip files. So like this zip file has the simple example of how a future works. So that was just a real simple example of what the meaning of a future was. This zip file here had all the examples where we're trying to read from 3 streams of a parent, where a parent would have 3 children process. A parent would have 3 streams, and we tried to do simultaneous I/O on the 3 streams. Okay, so we did it with threads and with futures and you know, a bunch of different ways. So those were all those examples that tried to read from 3 different streams in different ways simultaneously. This one here was just the example, the real simple example, just try to open a huge file and count how many bytes are in it. How fast can you do that? So that was just a few examples to try to read a file as fast as possible. And this is what we've been working on mostly, trying to do parallel searches of a large file. Okay? And I finally got a parallel search that's faster than the fastest serial search. It took, and I'm going to show you what I had to do to actually get some parallel speed up, and it wasn't easy. You know, it took a fair amount of thinking to get some actual speed up on a search. Because remember, the position we were at last week was we could write parallel code, and this is what you find. I was complaining that's in too many books. You find parallel code that uses all your cores, but then you realize that it's actually slower than what serial code would be. You know, they're showing you how to use the cores, but they're not doing especially a good job of showing how to use the cores effectively. And I can see why. It can be really hard to get things to actually speed up. Okay, so here's what, let me, go to the folder where I have the, and I put online the data that I've been using. So I finally got the data up there. Let me see, we're in this folder here. Okay, so here's the link to Andrew's data. If you download this link, it's all the data. And this link is just to this one, it's a zipped up version of this one 2.3 gigabyte file that I've been using. So I keep using that same file. It's a good size. It's big enough to be able to really get a sense of whether you're parallelizing things, but it's small enough that you don't wait 15 minutes for each run. So the slow runs are a minute or two, and when I finally got it working fast, the fast runs are about 4 or 5 seconds. So there's a nice spread of times. Fast is 4 or 5 seconds, slow is about a minute or two. So that size seems to work well for testing purposes. Okay, so this second link is to that file. If you want to, and I think it'd be real good, you could run this code on your computer and get a sense of whether you're getting the same kind of times I get on my computer. Okay, and then I wrote the program. We'll see, I've got 1, 2, 3, 4, 5 different sequential versions of it that are, that use just one thread. And then I've got what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different parallel versions. And just show you real quick, here's the fastest sequential version. So if I compile it, just give you a sense of here's what the final result was. Here's the fastest sequential version. it finds all the aardvarks in just under about 5 seconds. Okay. And after a lot of work, here is the fastest parallel version. It's, usually get it a little bit faster than that. Okay, I don't know if because of, I'm on Zoom right now. So the CPU is kind of busy, but so slow it down. But I get about, I don't know, 10, 15% improvement. Yeah, with using parallelism. Yeah, on a much bigger file, I mean, 15% improvement's not bad. See, I'm going from just under 5 seconds to just over 4 seconds. So, yeah.
That's scaling, though.
Hmm?
That's really bad scaling, though.
No, I'll show you. It's not as bad as you think. We're only using 2 cores.
Oh, okay. I thought you were
And
hitting like 12 cores.
I am, but they're not. I'll show you that okay, let me run it again. This was running on 12 cores, but now let me run it on just like 2 cores. It won't change. And I'll show you why.
Are you memory bottlenecked?
IO bottleneck. Okay. Okay, there actually, at that time it ran a little bit faster because probably just some quirk in the CPU scheduling. But see, it didn't, I went from 12 cores to 2 cores. I didn't get any slowdown. In fact, I even sped up a little bit because, and I'll show you how to analyze it. We'll analyze it real carefully and see that the key is that there's only one stream here. I'm reading one big file. So I cannot do much to parallelize the IO. Okay. The IO, you can't have 2 threads read from one stream. So really about all I can do is have 2 cores, one core doing the reading and one core doing the computing. Okay, there's really not much improvement. Now, when we switch to multiple files, then we can get, I think, then we'll see better speed ups. Okay, so let me, and just let me show you, like, here's the second fastest parallel version. Just to give you a sense. And the code is, this is going to take about, I think it's 30 seconds.
I made a bunch of attempts to be able to parallelize the code, like to try to get the same results of reading the 2 gigabyte file as I would loading all the individual files, and I just got killed by system usage.
I think it's impossible because you only have one stream, because it's one, unless you did something really clever and broke up the file on the hard drive by memory mapping it into different sectors, and we're actually able to like treat it as multiple files. So you'd have to play a game where you'd have to take the file on the hard drive and somehow pretend different parts of it were actually different files. I think you can do that.
I did something way more basic. I just used the original files and tried to read them as fast as the 2 gigabyte file, and I just got slaughtered with OS overhead.
Well, see, I haven't had a chance. I've been spending all my time just doing the serial one, the single file. I was hoping that when we switch to the multiple files, it could actually get a good speed up. But we'll see. Opening the files may be a problem. We may have to pre-open. We may. The opening 10,000 files is going to take a long time.
It wasn't that the system was waiting ever. It was that the OS was doing a huge amount of work to get those 10,000 file handles, because apparently that adds up.
Yeah, and to get a fair measure of things, you may need to pre-open all the files and then start the timing after the files are open.
All right.
Opening the files may just be a kill. But notice that this was about 15 seconds. So this was the second fastest, and so there's a huge difference in timing between the fastest and the second fastest. The fastest is about 4 seconds, and the second fastest is 16 seconds. And the second fastest is also parallel, and it uses all the cores, but just because you're using all the cores is not enough. You have to use them really wisely. And that's what's a killer about this is, it's not enough to just say, hey, I wrote a program, it uses all my cores. It's way more tricky than that. So let's start analyzing what these things are doing. Okay, it's only one file. So here's an outline of what's really going on. You're looping on a file, doing a read operation followed by a compute operation. The read operation grabs some data from the file, and we'll see that how much you've grabbed it can make a big difference in what's going on, but you're going to get some data from the file into a buffer. Then we're going to search that buffer for the word aardvark. So get some data in a buffer. So if I could say read operation into a buffer, and then here I'll search that buffer for aardvark. Okay, so read into the buffer and then search the buffer. Okay, now this is essentially the serial version of the program. You read, then compute. You read, then compute. Now the read operation blocks because it takes a while to fill the buffer from the hard drive, and then you compute. When this guy's blocked, you're not doing anything. You're waiting on the hard drive. And so there's the hope of getting some speed up, is that when this guy is blocked on waiting for the hard drive, why couldn't you be doing the calculation on, say, a previous buffer? Like you could be filling one buffer while you're analyzing another buffer. Okay, so that's this parallel up thing. The I/O operation would fill up a buffer, and then you would submit the compute operation with the buffer to a thread pool. So this would be submitting to a thread pool, and then this would create a new, this is the parallel version. The idea is these could be doing calculations while you're blocked, because then these are done. See, what happens is you would do an I/O operation. When this unblocked, you would submit it to the thread pool, and then go immediately start another I/O operation. Then while you're blocked, this one's computing in the thread pool. So now you've overlapped I/O with compute. So you might hope to be able to get some speed up there. Now, think about some timing. These numbers are just made up, but suppose that the I/O operation took 20 milliseconds and the compute operation takes 20 milliseconds. Suppose they take the same amount of time, okay? What happens when you switch to over here? So this is something that takes 20 milliseconds, and this, well, it takes 0 milliseconds here, because or some trick, but then it's actually going to take 20 milliseconds of CPU time, but on a different CPU. So this is 20 milliseconds on one core, and this is 20 milliseconds on another core. Okay, so this one takes 20 milliseconds, and this one takes 20 milliseconds. This was on one core. But this is the core is blocked. That whole 20 milliseconds, the core is actually just waiting for the data, and this one, the core is actually working for 20 milliseconds. But they're separate cores. So in this case, going from here to here will speed up your program by a factor of 2. Because you'd be perfectly interleaving the compute with an I/O operation. So if your I/O operation and your compute operation were the same amount of time, using 2 cores, you can get a 2 times speed up. Okay? Now, if you threw in a third core, it would be useless, because there's nothing for the third core to do. One core is blocked on the I/O, one core is processing the buffers that just got read. What's the third core to do? As soon as this core is done with the computing, this core is done with the I/O, so this core will just send its data to this core, so you'll keep 2 cores busy. So this is where you can see that a third CPU really can't even speed you up. If the compute time of the I/O operation, the compute time of the time of the I/O operation and the time of the compute operation are balanced, you can only get a 2 times speed up. Now think of another scenario. Suppose the I/O operation takes 20 milliseconds, but the compute operation only takes 10 milliseconds. Okay, so now what's the, think about what could potentially happen now when you go to the parallelize here.
Now you could have a third core, right, to work on the other 10 milliseconds of.
Right, and so now you can get well, actually, no, no, you
You're
can't.
presumably
It's processing
bottlenecked
it.
by I/O.
What will happen now? This guy takes 20 milliseconds and gives you a buffer. Then this guy's done with the buffer in 10 milliseconds, and he doesn't even have any more work to do.
So you want another buffer in that case, then?
No, you'd want another thing to do I/O operation, but since it's a single thread, since it's a single stream, you can't do 2 I/O operations at a time.
Oh, you can't?
No. Yeah, you can't have 2 people reading a file at the same time.
That's the serial version.
Yeah, no, it doesn't matter if it's serial or parallel.
Oh.
You cannot throw 2 threads at the same file because the file is read sequentially.
All right.
Unless you could do something real, and I don't know if some languages can do this, you'd have to have one thread reading in one part of the file while you had another thread skipping ahead reading farther into the file.
I think you can actually do that easily in Java. There are reader mechanisms that let you skip ahead into a file.
But that doesn't mean it'll speed up because you don't really know what the file system's doing.
I don't know if it's just moving the head on
right.
the disk, it might just be, like, well, I'm going over here now.
Yeah, it might just be, you can randomly access a file, but doesn't mean you can have 2 threads reading the file simultaneously.
Mm-hmm. And if it's a spinning disk and you're trying to read the same file from 2 locations, that's probably not going to work out well for you.
Well, you can. Because it would, because the 2 different locations of the file just look like 2 different files to the hard drive. If you tell it to read blocks 1000 and 2000, it can just read them in any order it wants. 1000 could be part of one file, and block 2000 could be another file, or block 1000 and 2000 are part of the same file. The hard drive doesn't really care. It just reads blocks. So it could be reading block 1000 from a file and reading block 2000 from the same file at the same time. It can't read them at the same time. It has to read one, then the other. Okay, but parallelizing the actual I/O itself is kind of tricky. That's why I was saying that when we go to multiple files, we could have one thread reading one file while another thread's reading another file, but we can't have 2 threads reading one file. Not that I know of in Java or C. If there's a way to do that, it's not something I've seen described in any books. Okay, so it might be possible with some trickery, but it's not part of the standard library. It's not part of the standard way of doing things. Though it might be something that some people can finagle out of a hard drive. Okay, so if the I/O operation takes longer than the compute operation, you really can't. You can get a little bit of speed up by overlapping this with this. You would get a 1/3 speed up. So now you would get a 1/3 speed up. Now here's a dramatic thing. Imagine that the I/O operation is 20 milliseconds and the compute operation is 1 millisecond. Okay. What happens now?
Do a lot of waiting.
Yeah. So when you go to the parallel version, what happens when you parallelize this?
You're going to need to queue a lot of I/O operations to keep your readers or processors.
No, you can't queue. You can only queue one I/O operation. It's one file. It takes 20 milliseconds to read a buffer from the file, and you cannot, you can't queue up another I/O operation until one is done. See, remember, I/O on a single file has to be sequential. You do one I/O operation at a time on a single file. Okay, the I/O operation takes 20 milliseconds, and the compute takes 1 millisecond. While one core is doing this for 20 milliseconds, the other core does this for 1 millisecond, and it's done. Okay, so what kind of speed up do you get by throwing 2 cores at it?
None.
Almost
Basically
none.
none.
Basically none. Yeah. When you go from serial to parallel, you really won't see any speed up. That's actually what's going wrong with a lot of these parallel versions that we've been writing. They're actually, I finally figured out a way to time them. They're actually this case. The I/O operation's way longer than the compute operation, and they're just, you throw 20 cores at them, and just the cores are really doing nothing. Yeah. So there's just this, if there's a real lopsidedness of the I/O operation taking much longer than the compute operation, you really don't get any speed up when you try to parallelize it. Okay. Now, here's a little bit interesting. What if it's the other way around? What if the I/O operation takes 10 milliseconds and the compute operation takes 20 milliseconds? Suppose you get a bit of data and it takes quite a while to process it.
Right. Then adding cores in parallel would help.
Yes. Yeah. Now you could. Yeah. Now if you would do one I/O operation. You do an I/O operation here that would take 10 milliseconds. You'd start up a core on a 20 millisecond operation. Then you'd go here and do another 10 millisecond I/O operation. Your first core is only halfway through its compute, but if you have a second core, you can launch it on another 20 millisecond operation. So you could, as long as you have some more cores, you could keep putting them in the thread pool here, and you could back up. You could even let the thread pool build up all you want, but you could actually get a lot of good out of your parallel cores now. If your compute operation on each buffer took longer than it took to read the buffer, now you can get significant speed up by having a thread pool and submitting the compute operations to the thread pool. Okay, so you can kind of see there's three regimes here. If the I/O and the compute are balanced, you can get a 2x speed up with two cores. One core for reading, one core for I/O, and one for computing. If the I/O is way slower than the compute, it doesn't even really much matter if you parallelize it or not, depending on how unbalanced. Well, if they're a little bit unbalanced, it's worth having two cores. If they're way out of balance, it won't even help you to have two cores. If the balance is the other way around, if the I/O is actually faster than the compute, then it benefits you to throw more cores at it. You can build up the computes in a thread pool, and you could be you could have multiple cores working their way through the compute time. Now notice you'll finish in the scenario like this, you'll probably finish reading the file way before the compute pool is finished with doing the compute operations. So you could probably imagine where you would be able to read through the file in a fairly short order, and you've just put into a thread pool, compute pool, all the work that needs to be done, and then your cores pull jobs out of the work queue and work through them as quickly as possible. But then you've got the I/O completely overlapped with the computing, so you're compute bound. So then instead of being I/O bound, you'd be compute bound, and you at least have the I/O overlapped with all the computing. Okay, so what's important is this ratio. Remember, this is the scenario where there's only one file stream. If there's multiple file streams, it becomes a different way of thinking. But if you're just doing one file stream and trying to parallelize the reading and the processing, then it all becomes a matter of which takes longer, the I/O operation or the compute operation. Okay, now what I did was I put some timing code into the parallel code. Okay, so here, let's look at this program here. Here's one of the parallel versions. Okay. Remember, the note said that there's a I/O part, and then you submit to the pool a compute part. Okay. Well, in here, it looks like this. Here's blocking on the I/O. Okay, so there's getting the I/O into this buffer C. Now, when we got the I/O into the buffer, we need to process it, break it up into, what this code does is it breaks it up into lines. Because if you want to search for the word aardvark, it helps to search for it in a line, because we don't count the word aardvark if it's split between two lines. So it's kind of useful to split the input buffer into the search for new lines. And also when we find aardvarks, we want to print out what line number they're on. So we get the buffer, process the buffer by finding line number, finding where the line endings are, creating a byte buffer out of one line, then submitting that to the task pool. So what we submit to the task pool, actually for every buffer we read in from the hard drive, we break it up into lines and submit tasks to the task pool for each line, okay? And this sounds reasonable. You know, read in a buffer, break it up into lines. Each line gets sent to the task pool to be computed, okay? And then for each loop, now this is the I/O loop, okay? This loop here is one I/O operation, okay? And then down here is the compute operation. This is the method that is submitted to the pool. What it does is it's given a line, and it just steps through the line, seeing if it finds the sequential letters. It's for every starting position in the line, it says, is there an A, A, R, D, V, A, R, K? And if one of these fails, you step to the next position in the line, and you're just stepping through the string, looking for the pattern A, A, R, D, V, A, R, K. Okay, so it's a real simple search of a line for that string. Okay, so it essentially does the search on the one line. Okay, so that's the compute operation. Okay, so the read operation is get the data, get a buffer's worth of data, but break the buffer into strings. I'm sorry, break the buffer into lines on the new line character and submit work tasks on one line. So the task processes one line, and the task is told what line number it's on. So if it finds an aardvark, it can say, I found an aardvark on this line number. Okay, so this loop is breaking the file into line numbers and breaking it into lines, and then giving each line, creating a task for each line. Okay, I want to know how long one of these I/O operations is versus one of these compute operations. So I'm going to use the Java Nano timer. This is roughly a timer that has a nanosecond precision, though you're constantly warned that depending on the system you're on, it may or may not really have nanosecond precision, but it's good enough for us. So nanoseconds, a billionth of a second, you know, that's supposedly on the order of one clock tick. You know, that's on the order of one clock tick of the CPU. But as a lot of people point out, that most of the modern CPUs aren't really, they're too busy. Essentially what it is the CPU is too busy calculating instructions to have time to go look at its clock. So when you call nano time, you're actually kind of interrupting the CPU. So this is not instantaneous, but it's still pretty accurate. It's way better than a millisecond timer. Millisecond timers are useless. Nanosecond timer is not too bad here. Okay, nanosecond timer is not, is reasonably accurate for measuring a quick loop like this. So you start the nanosecond timer, you do the I/O operation, stop the nanosecond timer, and then print out how long did it take from the start time to the end time.
Oh.
Okay. Then loop around. Okay. Mm-hmm.
I did build a really, really advanced timing library for particularly measuring nanoseconds with Java.
Mm-hmm.
I was able to get milliseconds from the normal milliseconds call because I know those are going to be very consistent over long periods of time, but also grab nanoseconds and just put them into one long timestamp that should be accurate over long periods of time.
Well, the problem is it's only accurate up to how good the CPU is at doing this. The warning is that the different CPUs are just more accurate about telling you nanotime than others.
x86,
so you're at the mercy of the CPU.
x86 across the board uses the high precision event timer, or HPET.
Well,
it's
okay,
pretty accurate.
Yeah, but this library may not be. Yeah, so you're at the mercy of whoever wrote this library, and
that's true.
Yeah, and since this is Java, and Java tries to be write once, run anywhere, yeah, there's a little bit of there's a fair amount. if you write real low-level C code, you can actually drop into assembly language and get really accurate timing because you could talk to the CPU as directly as possible. This is as good as Java is going to get. So, you can't unless you write your own assembly language code and try to merge it into your Java code, which is possible. Using there's ways of writing your own assembly language code and merging them with the Java bytecode, but that's way beyond our what we want to do here. This is as good as you can get. The system nanotime is about it. I don't think using pure Java, I don't think you can get any more accurate than what this is doing right here. End time minus start time. But in C and C++, especially if you're willing to write your own assembly code, or if you just go get like you say, if you write a good library, you can get things that are probably pretty accurate. Okay, but this is as good as Java is going to get, and it'll tell us information. It's going to help us. Okay, so here we're printing out how long one I/O operation took, and down here we do the same kind of thing. We start a compute time. We measure the start of the compute operation, measure the end of the compute operation, and print how long the compute operation took. Now, when we print these out, we'll be printing out gazillions of results. So this is going to throw off the time. It makes the program useless, but it lets us run it for a little while and get a rough sense of what do our I/O times look like compared to our compute times. Okay. So if you compile this and run it, okay, I just stop it here, okay? Just by clicking in this window, I stop the program and I can scroll through the output. And you can see where we are right now, okay? Oh, I got it. No, here it is. The reason that there's a lot more compute times than there are read times, because remember, each time I read a buffer, I split it into lines. So a buffer might hold anywhere from a couple to a few dozens of lines. So every read operation branches off a lot of compute operations. But look at the massive difference in time. The read operations are on the order of 7,000 nanoseconds. And the compute operations are in the order of 1,000. There's a massive difference in time between the read. We're in this regime we said earlier where these times are way bigger than these times, and we can't parallelize it. We actually have the situation where it takes way longer to read a buffer than it takes to process the buffer. And you can see that here, that the read times keep showing up as really long, and the compute times are, some of them are actually, even with the nanosecond timers, some of the compute operations are really short. Sometimes, like if a line is only 5 characters, one of these compute operations is going to take next to nothing.
Or zero.
Yeah, there's even some, see, that's probably a line that actually had no bytes in it or 3 or 4 bytes in it. Okay, so we've got a phenomenally lopsided, we're in this regime here where we have a phenomenal amount of lopsidedness between the I/O operation and the compute operation. So we're not going to get any speed up from the parallel thing. Parallelizing it doesn't speed it up at all. You do make your cores busy. The cores get busy doing all these compute operations, but they're completely overlapped with we're completely I/O bound. While we've got all the cores doing these little 1 millisecond compute operations, there's one core just sitting there waiting a long time to get the next I/O operation. Okay. All right. So now let's look at the better version of this program. Okay. Go over here and get the timed version of the fast parallel one. Okay. Now this is the fast parallel one, and it's got the timing data in it. So we're only interested in the timing data. We want the relative balance between how long it takes to do an I/O operation and how long it takes to do a compute operation. Now, here's what this program did. If you go back over to here, if you think about why is the I/O operation taking so long, and it's a combination of a couple things. First of all, you have to wait for the I/O operation to happen, but then you're doing a bunch of processing of the I/O. You know, so you're doing some of the compute work in the I/O loop. So the I/O loop is waiting on the I/O and then it's counting the lines. Okay, so I realized that that's actually probably a big part of the problem, is that I'm doing too much work in between creating the tasks for the executor pool. I'm actually doing a fair amount of work on the buffer, and this is serial code. Okay, so the trick was, when you get a buffer, just pass the buffer to the compute task, not do any work on the buffer. But it doesn't, it's turned out to be a little bit trickier than that. But the idea was to do as little work here as possible to try to shorten the I/O time. Try to put as much work as possible in the compute ones, because we saw that the compute ones were already tiny, really short. So make the compute jobs longer and try to shorten out the time over here. Okay, so here's what I managed to do. Okay, read a buffer. Okay, send the whole buffer to the compute pool. Notice that I just read in a buffer and send the buffer immediately to the compute pool. Okay, so the compute pool, the compute task has to process the buffer. But now I have a problem. I don't know what line number I'm on anymore. So after I submit the buffer to the compute task, I still need to do a quick little process through the buffer of how many new lines there are, because I need to know how many line numbers there are. I need to keep track of what line number I'm on. Okay, because if I don't keep track of the line number here, then there's no way to tell each task, are you in the beginning of the file, the middle of the file, or the end of the file? This guy's got to keep track of line numbers. Okay, so read in a buffer, send the whole buffer to the thread pool, but then after you sent the buffer to the thread pool, do a quick scan of the buffer to see how many lines there are and update the line counter. Then allocate a new buffer, because if you've given the buffer to the task pool, you can't reuse it, because now that buffer is holding data that the task hasn't gotten to yet. So allocate a new buffer and then go read more data into that new buffer. Okay, so read a buffer, submit it to the task pool whole, scan the buffer real quickly to see how many new lines were in it, create a new buffer, and then do that over again. And also time how long that took. Then down here, the task, now this is kind of interesting. This is, when I got this working, I was surprised how this is actually demonstrative of something you see all the time. I have to count the line numbers again, because when the task is given a buffer, he's told what the line number is at the beginning of the buffer, but as he processes the buffer and finds lines in the buffer, he's got to keep track of how many lines he's found in the buffer. Because when he prints out what line number it is, he has to know what line number he is. So the line number he's told was the line number at the beginning of the buffer, but he has to count the line numbers again. Now, see, this ends up being real typical. When you break work up into parallel code, it's not at all unusual to find yourself having to do the same thing two places. Notice I'm counting line numbers in the buffer there, and I'm counting line numbers in the buffer there. So then you go, well, that's stupid. Why are you going to do the same thing twice? And the answer is, I have no choice. The logic of the code is demanding that I have to do a calculation in two places. And that's real common when you write parallel code. You find yourself having to do redundant work in a couple different places. It turns out to be sometimes faster to do redundant work than it is to try to do the work in one place. And this is actually a very common problem with parallel code, that you find yourself doing the same piece of work in two places. Scan the buffer for new lines. That's done here to keep track of how many lines through the file I am. And then scan the buffer for new lines so you know what line number you're on in that line. But here you're going to add, now you're incrementing the line number you got. You knew the line number that was where the beginning of the buffer was, And now you have to keep track of how many lines you've gone through in the buffer. So you get this little bit of redundant code, okay? Right? But remember, this is 3 times faster. Even though I'm doing redundant code, it still turns out to be faster, okay? And we'll see why. Okay, now I'm gonna run it. I wanna run it and see how the amount of time of one loop of IO is compared to how much time one loop of compute is, okay? So compile this, process it. Okay, stop it and just look. Look. And what turns out, it turns out real interesting. Our read times and our compute times, look at them. They're almost balanced. They're very close. They're not perfectly balanced, but they're in the same order of magnitude. We've gotten ourselves into a situation where the compute time and the read time are pretty close. You know, they're on the order of 100,000. You know, they're on the order of around 1 million nanoseconds. See, 2 million, 1 million, 5 million, 1 million, 1 million. You know, 1 million, 500,000, 1 million, 500,000, 1 million. So you know, it's actually kind of works out pretty well. You know, we found by luck. Actually, I have to say this is really by luck. By luck, I found a way to write the code that kind of nicely balanced the. We think of it in terms of this. I found a way of actually getting a balance between the read operation and the compute operation. And actually, to tell you the truth, it was more by luck, I think. I mean, I was just trying things. I knew that that's what I was trying to get at. You know, after thinking, I realized that the problem was we were actually in this regime where the IO operations were completely dominated the compute operations. And I needed to kind of find a way to break the code up where these things were more or less balanced. And this code here did it. You know, this code here of reading one buffer. Oh, and playing around with the buffer size also helped a little bit. You know, changing the buffer size will you know, there's a little bit of playing around with buffer sizes here. So right now with this buffer size, and if you might even be able to find a better buffer size, but with this buffer size, I got a reasonable balance between one read operation and one compute operation. So now if I've got a balance between the read and the compute, I can throw one extra core in there and get a speed up. But if I throw 2 or more cores in there, it doesn't do me any good. And that's exactly what I find. I find that when I run this program, if I give it 1 or 2 cores in the thread pool, it runs fine. And if you put 5 cores in the thread pool, no more speed up. Yeah, and you can see why. Because you know, there's about a balance between the IO and the compute. So there's going to be no point in giving it more cores. Once it's got one core for IO, and I give it a couple cores for compute. So occasionally, sometimes maybe a compute operation is a little bit slower. Sometimes a compute operation is a little bit faster. So it seems like it doesn't mind having 2 cores for compute operations, but even 3 or 4 cores for compute operations do no good at all. No good at all. Okay. All right. So you know, by careful analysis of what's going on, you can kind of get a feel for what's needed. What was needed was balancing IO with compute. And then with a little bit of luck, I was able to find a balance of code that did give me just that, you know, that gave me just that good balance between how much time it took to do one read loop and how much time it took to do one compute task. Okay. Now, when you switch to multiple files, then you don't have to, you know, then the analysis becomes completely different. Here, this analysis is driven by the fact that I'm just doing one file. You know, I've only got one possible IO stream. You know, I can't have multiple IO operations going on my file, so I can only have one thread doing IO. But you know, I could possibly have more than one thread on buffering. But unless I could get into this regime, see, I don't know if I could. You know, what would be ideal would be to get into this regime where the I/O operations were consistently faster than the compute operations. Now, maybe you can get to that by having a, well, let's try it. What if we give it a huge buffer? If we give it a huge buffer, maybe the I/O operations can become much faster than the compute operations. Let's go ahead and just give that a try. Okay. There's a huge buffer. Okay. So let me compute, see if this has any effect on it. Still pretty balanced. The buffer size didn't, I think the buffer size, in this case, this is one place where changing the buffer is not going to help too much. They both got longer, but they kind of scaled together. You know, they're still in the same order of magnitude. You know, the compute times and the read times are still in the same ballpark, the same order of magnitude. So we're still, now actually, so let me go to the non-timed version of this and give it the same buffer size so I can actually run it. So this one's the one that actually runs. Okay. Give it that same buffer size. Go ahead and run it. My guess is it's not going to speed up. And it actually seemed to maybe slow down a little bit. It went from 4 seconds to 5 seconds. Now, that may just be a quirk, but it didn't speed up. You know, increasing the buffer size by a huge amount didn't somehow make it, and it, you know, I don't know if there's any way to get into this regime where we could get the I/O reads much shorter than the computes.
There is a way to do it, but it's based on your hardware, not your software.
Well, I was just going to say, let me move this whole calculation over from my machine here has, I haven't tried this yet. I've been meaning to do it for a while. The drive we're on right now is a solid state drive.
Mm-hmm.
And over here is a spinning platter drive.
Oh, that's going to be much slower.
Yeah, it'd be, okay, let's just do it. Let's move it over to the spinning. Let's move this whole folder over to the spinning platter. It'll take a second to copy it.
I have a question.
Yeah. Mm-hmm.
Can you read from the beginning of a file to the middle and the end of the file to the middle at the same time?
Well, that'd be the kind of, yeah, that's what I was saying. Like, if there's weird tricks you could do to try to have 2 people reading from a file at once. As far as I know, I don't know of any way to do that. You know, it sounds appealing.
Yeah.
But I don't know of a way to do that. I don't think the file systems are very well set up for that, but they might be. There may be some very sophisticated ways of using the file system where you could read one file, or you could read a file starting at read it backwards. You know, right. Read through the file backwards. You know, it might be possible. You know, let's see. Well, if you Google now, you can always do it the slow, idiotic way. The slow, idiotic way is use the seek function to seek to the end of the file, read it, then seek to almost the end of the file and read it, then seek to not quite the end of the file and read it. But that will be absurdly slow because what you're really always doing is starting at the beginning, seeking to some place, and then reading. Yeah. Right. So that's probably not at all going to be. You really want to be able to sequentially step through the file, starting at the far end, going backward. you'd have to read these to find out if they're doing the seek thing or if they're actually if they have a clever way to read a file backwards. Because I know that you can use the seek function to just put yourself anywhere in a file.
Right.
Yeah, but that's but seeking into a file is a slow operation itself. So yeah, but that's what that would give you 2 threads into a file, and one thread could be working from the file from beginning to the middle. One could be working from the end to the middle. You've double your speed.
Right.
Okay. Question is whether whether there's an effective way to read a file from the far end towards the middle. I've never tried doing it, and the only way I know to even think about it is with seek, and that's not going to be fast. Yeah.
Right.
Yeah. Okay.
Yeah, that wouldn't make sense to start from the beginning to go to the end and go back every time.
Yeah, but that's what you do. It's like a linked list. Like you can read a linked list from the end to the beginning, but it tends, you usually end up doing it unless you have a tail pointer.
Right.
You have to do it by scanning from the front to the end and find the end, and then you have to start the front again. Now I don't know if file systems give you like a tail pointer so that they have a pointer at the end of the file that they could read backwards from. It would
Depends on the file system.
Right. It's going to depend on the file system. The answer might be that you could do it with some file systems, but not other file systems. So like maybe you could do it with the NTFS file system, but you can't do it with the what's Linux's file system called?
ext4.
ext. Yeah, maybe or maybe you could do it with ext, but you can't do it with NTFS. Who knows? Yeah, but then your code would be dependent on the file system, which is not very good code. Yeah, you don't want code that says, oh, it only works on Linux if you use this one file system, which is okay if you're running in a server environment where you can control everything, where a company can say, all our servers have this file system, so go ahead and use that file system as efficiently as possible. That's the difference between writing code for running on laptops and writing code to run on servers. When you own the server, you can dictate the environment on the server, and you could optimize for that one environment. They do that all the time on Purdue's like supercomputers. They know exactly what environment every supercomputer node is running, and you can optimize for it. Okay, but on a desktop machine like this, who knows what file system is running on that desktop? Okay, so the answer might be file system dependent, and you might be able to do it, but have code that's file system dependent. Okay, all right. All right, now the code is over here on the spinning platter. Okay, so let me run it on the spinning platter. Okay, so here's the fastest parallel version was that guy. I'm going to run it on the spinning platter.
Huh.
Not much difference. Huh? I was expecting to be I was expecting there to be a bigger difference. Not much difference at all. Well-designed spinning platter. Okay.
It might be that your
cache. Yeah.
It might be cached.
Yeah, that file may be. I'd have to reboot the computer to find that out. It could be that that file, it's a fairly large file, but it might be reasonably well cached, though. That even though it's on this, even I went to the spinning platter. One thing I could do to, I don't know how dumb the caches are.
You might just be able to load up a whole bunch of stuff.
Well, no, give it a different no, giving it a different name probably is not going to fool it.
Almost certainly won't do it. The name is just for us.
Yes,
mostly.
Yeah, the name is it's like a reference to an object. When you change the name of the reference, you're not changing the name of the object. So
and
this is
the
now
object is what's stored.
Right. So this is just changing the name of the pointer to the file. The actual file is the exact same file, and the file system knows that. On the other hand, if I did on the other hand, if I did here's what I could possibly do: make a copy of it. The copy won't be cached, and then let me read the copy. the file system probably is not smart enough to realize that the copy is, that it could, it's not going to be able to use the cache of the previous version as a substitute for the cache of the copy. So my guess is the file system's not that clever. Okay, so there's a copy. So now let's see if the timing ends up being any different. Okay, so we're on the spinning platter, and I'm going to run it. Same time.
On your system, it might not even matter if you do a reboot. You might have an Optane stick in there.
Yeah,
Optane sticks are non-volatile.
Yeah.
So they'll cache.
Yeah.
And they're almost as fast as system memory.
Yeah. Yeah.
But they're not going to die after a reboot.
Does Windows keep its cache across reboots? I kind of doubt that.
It wouldn't have to.
Yeah. What this brings up, one of the hard things about teaching a course in parallel programming, there's a couple hard things about it. One is, as I pointed out, just because you've occupied all 27 of your cores doesn't mean you've done anything. It's easy to write programs that occupy all the cores, and you can actually write code that occupies all the cores slower. Okay, we've seen that now. The other thing is that a lot of times when you really want to know how to speed a program up, you have to start asking questions about the hard drives and the hardware. You really start, if you actually want to really take a concrete problem like this we've done here and say, how fast can it be? You almost inevitably end up asking questions about hardware. Because if you, unless you don't care about getting it as fast as possible, but if you really care about getting it as fast as possible, your answer is going to be depending on hardware. You're going to be asking, about caches and whether it's a spinning drive or a solid state drive. So right now, like for example, right now, this program searches a 2.3 gigabyte text file for the word aardvark in around 4 seconds. I had no idea if that's as fast as it could be done. Can somebody who knows a whole lot more about this than me come in and cut that time in half? I have no idea. Yeah.
The biggest limitation for this sort of a process is going to be your disk I/O.
Well, I know that I can count the bytes in the file in half a second because I've got the code that does that. I can now that's only counting the bytes. It's not looking at them. But in terms of getting the data off the hard drive into memory, it can be done in half a second. Okay. So now if the data can be got into memory in half a second, how much time does it take to process it? To count, to look for the aardvarks? To go from half a second to 4 seconds doesn't sound, I think this is about as fast as it's going to get. Yeah, I'd be surprised if it can be cut in half again. Maybe you can get, maybe someone who knows a lot more can get it from 4 seconds to 3 seconds, but it takes half a second to read into 2 gigabytes, just to count the bytes in the 2 gigabyte file. Okay, but that does not look at the bytes; it just counts them. Okay, so I think this is probably pretty close to being as quick as it can be. It's certainly. You're not going to get it less than half a second. So right now it's down to about 4 seconds. Considering it started off at about a couple minutes, yeah. I remember that one of the interesting baselines was what TextPad could do. Remember, TextPad could open that file. TextPad can open that file in about
a while.
Well, no, I think my memory is about 20 seconds. So you notice how it kind of just pops up. Okay, so it opened the file in about 20 seconds, and then it could search the file. I click on Mark All, and it'll look for all the, and it takes about another 30 seconds. Okay. And I believe TextPad is single threaded. It's hard to know for sure, but I don't think it makes use of all the cores. So notice that it's finished. It found all the aardvarks, and there's about 15 or 20 of them. I forget. Yeah. And you can also double check our answers over here. Yeah, if you use TextPad, you can verify the answers. Like it found an aardvark on line 216. There's that one. See, 216, 13791, that's this aardvark here. Okay, that aardvark there is that line number there. And then the next one, see, is 467. So you can double check that the answers are right by comparing our results with what TextPad does. So when our parallel programs were taking 2 or 3 minutes, I knew something was really wrong, because TextPad could do the whole thing in well under a minute. 20 or 30 seconds to open the file, 20 or 30 seconds to do the search. But now we beat TextPad. Now we're doing it in 5 seconds. So we have beaten TextPad in doing this, but TextPad is doing TextPad is doing searching using a much more powerful mechanism. It's actually doing, you can do regular expressions. So it's doing searching in a much more powerful way. We're just doing simple, stupid search. So we're not doing a sophisticated search, but we got it down to 5 seconds. Okay. All right. Now, let me clean up. Okay. If you go back through the other parallel programs, you just, like if you look at the very first one, they were naive. They looked like they were reasonable, but like, okay, this one, that one's parallel, and it's going to take forever. I can't remember. This is one of the ones that takes several minutes. And I think this is one of the ones that, makes us feel real proud that all our cores are working real hard. And they're working real hard to take a ridiculous amount of time to search the file. Okay, you can see all the cores are working hard, and it's going to take a long time. And what's going wrong here is, this case, I think what's really going wrong is it's just using too many high-level libraries. Being unwise about what libraries are using. So use a scanner to read next line from the file. So that's a pretty high-level I/O operation using next line on a scanner. Okay, then we just give that line directly to the thread pool. Okay, so then the thread pool's got a string. Then the thread pool says, okay, I know how to search a string for a word. Split the string using this, split the string, then search through the tokens and see if you have use the string index of function. Notice that I don't have to write any code. Split the string, use index of to find the word aardvark in the string. So I'm using very high-level library functions, and it makes the code very correct and very easy to write, very short. And I have the pleasure of seeing all my cores busy, but I'm just making my cores do massive amounts of work that they really shouldn't be doing. This is one of the things that makes parallel programming hard. How do you know when you're how do you know when you're killing yourself with higher level functions that are just using up you're using up your cores to do high level functions? Okay. This is going to take a long time. And it looks like the right thing to do. I mean, it actually kind of looks right. Scan in a line, fork a process to process the line, scan in another line, fork a process to process that line. It looks like you're overlapping I/O with compute, but the whole thing just bogs down, just completely bogs down. Okay, and if it's worth, I think, reading these things to see how I'm doing what I think is pretty much reasonable steps to speed things up, and it takes, but the reasonable steps didn't get anywhere until finally started really thinking hard about balancing the I/O with the compute. It wasn't until the I/O was balanced with the compute that things could, and then that started writing everything in real low-level code too, like this one here. This is a pretty split and index of really looks like overkill. Okay, and it is. So the second version gets rid of the split. It still uses the scanner to read in one line, but instead of doing a split and then index of, it does just this, which is actually very easy to write. It just walks the string, and it uses char at on each. So it just says, is the char at I A, I plus 1 A, I plus 2 R. So it just does an if statement here. And this actually speeds things up quite a bit. So getting rid of the high-level split, then stepping through the tokens and looking at each token, going to this did speed it up quite a bit. This one's running forever. This one's really absurdly taking a long time. This one is quite a bit faster. Okay, and it got rid of some high-level code for some still very simple. I mean, this isn't very hard to write. Very simple, lower, but it's still at a lower level. It's saying, notice that this is going to be harder to change. If I want to search for a different word, I have to. It's kind of tedious to go change that compared to what it would be like to change this. Notice that this could even be a variable. This could have been a variable. It's kind of hard to set a variable here to be what you want to search for. Mm-hmm.
I just sent you a version of my search program, and it might actually break 4 seconds.
Oh, okay.
You mind trying it out on your computer? Because it's going to be a lot faster than what I can manage on mine.
Oh, I don't have time to even grab it. I'd have to, let's see. I'd have to log into my email to get it. And that takes me, I have to get out my yeah. I'll look at it.
Okay.
Yeah, and we'll look at it on Wednesday. Yeah, I'll look at it. So is it Java?
It's Java. It uses standard in to read the file, and you can give it any word to search for.
Okay, but what speeds it up?
I'm using futures, or well, not futures, but a executor service.
Well, we already we're using an executor service here also. Yeah, unless this fast one was using an executor service. It was using standard in. Yeah, it's reading from standard in. See, there's the loop, reading buffers full from standard in, and it submits the work to a pool. Oh, I'm sorry, where is it? There. Oh, there. See, it's using a thread pool. It's a executor service type thread pool. Okay. So yeah, unless there's some little difference. I mean, I can imagine that there's something. Maybe maybe you found if you got one step different than I do that makes things more efficient. Yeah.
I'm not using task. I'm using runnable, and I'm not using execute. I'm using submit. So maybe that's it.
I'm using runnable. Okay, you're using which one?
Submit.
And I'm using execute. Oh, okay. There's
but
a
I'm
difference.
Also not using the future that it returns because for whatever reason that blew up on me. So
well,
I'm
you don't
just
need
using...
the future because once it's done, it's done. So yeah, submit returns a future. Execute doesn't return a future. And so
yeah, so I store all of the runnable tasks that were created in a stack, and once I'm done, once I'm await termination releases, I just run through that entire stack and add up all the counts from the individual objects.
Okay.
I
Yeah.
have no idea if that's ideal or not.
No, I don't
but
either.
it ran in 6 seconds on the machine that I'm using, and I know
Okay.
your SSD is way faster.
Yeah, well, no, when we switched from the SSD to the hard drive, didn't change speed really. So who knows if it's really, yeah. Oh, yeah, you're in this, yeah, it'd be interesting. It'll be interesting to compare it. I'll look at it because there's those kind of differences. Unfortunately, small differences in code can make big differences in timing here. You never know when something really matters. So changing the executor service, changing from pool.execute to pool.submit might end up being, might just give a little edge. It might be worth a little edge. Yeah, like for example, this is reading from standard in. Here's the same code reading from a file stream instead of reading from standard in. See, when I run this one, I run it by redirecting standard in to the program. Okay. This one just opens the file directly. It opens the data file. Okay.
I ran into the same issue where on Linux, where for whatever reason, reading from standard in is way faster than any file reading facility I can find in Java.
I've had mixed. Some of my programs are faster when they read from standard in, and some of them aren't. Yeah, and like this time, it didn't make much difference. I ended up with, well, I think the standard in was a tiny bit faster. Yeah. I think for some reason I think standard in is a little bit faster than reading from a file. Now I'm not really sure why that is. A file input stream is not buffered. A file input stream is not buffered, but I'm doing my own buffering here. So the fact that the file input stream is not buffered doesn't really matter. Now standard in is buffered, but I'm essentially bypassing its buffer because I'm actually reading directly from standard in with a buffer that's bigger than its buffer. So the way I understand it is I'm bypassing standard in's buffer here. So the fact that standard in is buffered and file input stream is not buffered shouldn't matter here. Okay, but it does seem that file input stream is a little bit faster than, does seem that system.in is a little faster than a buffered input stream. Okay, weird little things can matter sometimes. Okay, all right. The next time we're going to try to switch to the massive amount of files and see if that changes anything. Like right now, this file here is 10,000 files. I think it was 1,000 files. There's 1,000 files in that one file. What happens if I just read the 1,000 files? Okay, the 1,000 files are in this folder here. Yeah, so these are the 1,000 files that were bundled up into this guy. Okay, will it be faster or slower to try to read the 1,000 files? Same data, so the same number of aardvarks, but will this end up being faster or slower? Can you parallel? Will it be harder to parallelize across 1,000 files, or will it be easier to parallelize? I don't even know. I'm not even really sure yet. Yeah. So that's what I'm going to try next. Is we'll do experiments. We'll see. This is the same data that's in this file here. Here it's all in one file. Here we'll be able to open lots of streams, but at the same time, I have a feeling that the idea will be to come up with an effective strategy that has essentially a pipeline where we have one thread opening files, one thread reading from, then multiple threads reading from files, and then multiple threads processing the data. But then, while you're opening files, one thing can be opening files while one thing can be reading from files while one thing can be processing the data. And then maybe that'll get all interleaved with 12 cores We'll see. Okay. So that's my feeling is that this may be able to be fast, but we'll have to, find an effective strategy where it won't be just open 12, opening 1,000 files will take too long. But maybe if the openings are interleaved with the reading, maybe you can open 1,000 files. I have to see how long it takes to open 1,000 files. It may be that with 1,000 files, you can't do it. 1,000, these are fairly small files. It may be that 1,000 small files is impossible to work with. I have a feeling that might be what we're going to find out, that it might be impossible to work with 1,000 small files.
It occurs to me that it might be faster to try to buffer an entire file before you start touching the data inside of it for processing.
We'll see. Yeah, there's different. That's where this is challenging. There's no, I can't think of an obvious strategy that's going to read 1,000 files as fast as possible. So it's going to be a little bit, just like it took a while to come up with the parallel strategy to read even one file. It was not trivial to come up with the parallel strategy to read even one big file. So it may take a little work to come up with an effective strategy for parallelizing lots of I/O. Okay. Yeah. Okay. Well, we've reached the end of the time. So I'll go ahead and end the meeting. If you have questions, let me know. Okay. Bye-bye. Good night.